us talk about the determinant of a matrix. This is chapter 2 of the textbook, and it is a third week of the syllabus. So when we are talking about the determinant of a matrix, first we refer to a matrix, which means it is basically 4 elements, 2 by 2, and we refer to each element of the matrix by the row and column numbers. So as one can see, the first row, the top row is first row, and then second row is the bottom one. So it is 1 and 2. The first subscript is referring to the row number. That's why this is first row, and then this second row. And then it will go to the right. Other elements of the row will be referred by the column number. So it's like 1 and 2. That's why element corresponding to this location is 1, 1, and this is 1, 2, and this is 2, 1, and this is 2, 2. By this name convention, we are able to refer to any elements of any size matrix. So we will talk about two-dimensional matrix right now, and after that, we will generalize for the bigger dimensions. So let's go back to our determinant. So now determinant is shown as determinant of A, matrix A, is equal to the multiplication of the cross elements and subtraction between them. A11 times A22 minus A21 times A12. I will write again. So determinant of A is equal to A11 times A22 minus A21 times A12. Means if they look about the locations, so this element times this element minus this element times this element. So this is a cross and this is a cross. We have to memorize this. So we will generalize this for the bigger one, n by n or 3 by 3, and then simplify to the one-dimensional. One-dimensional means you will talk about just one element only, and that's itself, determinant itself, A11. So here we go to, we don't go to proof of this. Just the idea is if this determinant is not equal to 0, then the matrix is not singular. When it's a 0, it is singular. We have to memorize this. A is non-singular. A is non-singular. If determinant A is not equal to 0, which is in the book. As you see, A is non-singular if and only if determinant A is not 0. We have to memorize this by heart. We will use it a lot. So when we go back for the numerical implementation, is a matrix. There are 4 elements, and then instead of A11, we are saying it is 3 over there. So A11 is a constant, which could be any number. It is generalized. And now we are saying that it is specific 3, 4, 2, 1. So when you are talking about determinant, we show the number, the matrix in number form. We show it by this way. Just parallel lines, and this means the determinant of this matrix. So if there is a matrix which is just cross, curly, like curly, or actually cross like this, the square bracket, then this is a matrix, and then we cannot say what is it. It's directly matrix itself. But when this is written on the left-hand side style, there are 2 parallel lines. It means it is talking about the determinant of A. So this is determinant of A. And this corresponds to a number. What is that number? Based on our formula above, we see A11 times A22, it means multiplying this by this 3 times 1 minus 2 times 4 equal to 3 minus 8 equal to minus 5. So when we generalize to the higher dimensions, we will not go to the proof, but we have to understand the concept is similar. Whatever the way is, when we calculate the determinant of A, it can be higher dimension or lower dimension. We are talking about if this is equal to 0, it is singular. If not 0, it's non-singular. That's it. So we will go back to generalized formula of the three-dimensional. In three-dimensional matrix, we are talking about a minor and cofactor to be able to calculate the determinant of the matrix. So let's go to the new page. So three-dimensional matrix we're talking about. Three-dimensional matrix means generally it is something. I am looking for an example here. I will take the screen and copy it and put it here. So now we are talking about some definitions to be able to calculate the determinant of three-dimensional matrix. So first we call it minor. Minor means in definition here, deleting the row and column containing AI means we are talking about, let's say we are talking about this part, the minor of A11. The way you do, you just take it out and take it out. Then whatever left here is the minor of Aij, means any row, any column, any location, we have the element Aij. In this case, let's say A11. Then the minor of Aij is called Mij, and Mij is basically A22, A22, A23, A32, A33. So this is the minor. And the determinant of this one is the minor actually. So determinant of this one. And we know that this is from the above definition A22 minus times A33 minus A32. We are not able to see it. Times A23 means multiplying these two, subtract these two. And this is the determinant of the section of the matrix which is left out when you cross out the column and the row of the element we are talking about. Here we are talking about Aij. Then, assuming that row and column is not there, what is remaining is the matrix which we are looking for as determinant of that one is the minor of Aij. So minor of A11 is A22, A23, A32, A33. So minor is Mij is equal to determinant of A22, A23, A32, A33. It's clear. Now it means this is a number basically. And cofactor is another definition. Cofactor will be called Aij. Cofactor is belonging to Aij, and the way it works is Aij is equal to minus 1 to the power, we will talk about the details, determinant of Mij. Now, determinant of Mij, we talk about it. Just multiplying a certain number means bringing the sign to it makes it cofactor. And this cofactor belongs to a location. In this case, it's Ij, generic. So if it was 1, 1, let's go to next page. New page after. Let's go back to here and say we talk about a minor of A11. Minor of A11 is M11, which is equal to determinant of this part. Determinant of A22, A23, A32, A33. This is minor. And that's equal to A22 minus times A33 minus A32 times A23. Now, a cofactor is just adding the dimension to it. So it was Aij, so now Ij is equal to 1, 1, right? A11 we are looking about. So this is A11. We are talking about the A, capital Aij means cofactor of this location. So cofactor of the location is calculated by the minor and the sign. So the minor is defined here, and the sign will come. Let's make the sign first. Aij in this case is 1, 1 is equal to minus 1 to the power I plus j, 1 plus 1 times determinant of Mij, M11. What does it mean? It means this is bringing a sign, and when it is even power, this will be positive. When it's an odd number, it is negative. So in our three-dimensional case, we are talking about if it is belonging to the first element, it is plus. If it is belonging to this location, it becomes minus, because first row, this subscript addition is 3, odd number, minus 1 to the power odd number will be minus 1. So this is minus, and then this is plus. This is the way you will use it. And this is giving the definitions of minor and cofactor. Minor and cofactor, we have to memorize them. So when we are talking about determinant of the A in general, we are saying that there should be a definition somewhere here. It's here. Let me take this screen to the outside. This is our definition of determinant. You take a row, and for that row, you take each element, and it is cofactor. Multiply them and add them up. So in this case, we are taking. Let me see if I can change the color. Let me make it red. So now A11, we are taking the first row, A12 and A13. So it says determinant is equal to these elements multiply by their cofactors. So what's cofactor of 1, 1? We talk detailed about. We say assume this line and the column and the row is gone. Then this is the matrix we are talking about for the minor, and minor is here. Determinant of that minor matrix times a sign, minus or plus based on its location. If it is 1, 1, then it's plus. If it is 1, 2, it is minus. So this brings a sign for the plus, and this brings signs for minus and plus also. So in this case, A11 times the matrix, the determinant of this matrix is A22 times A33 minus this 2. Similarly, when we are talking about the A12, then the cofactor Aij12 is equal to minus 1 to the power 1 plus 2 times determinant of the minor, 1, 2. And what is that? Let's go to new page. Control D, I think. Yes. We are talking about this, and then let me take this this one again. I couldn't do it. I will do it from here. Now, talking about the cofactor of A11, which is this one, A12, which is this one. I will show it in different colors. Now, A12 green. The cofactor of A12 is this and this. It means A21, A23, A31, A33. How was it? You remove the column and row of the element you are talking about. This is 1, 2. So we remove 1 and 2, the first row and the second column. And the elements left are 2, 1, 2, 3, 3, 1, 3, 2. So this is the minor. And determinant of this one times the coefficient, which is making the sign negative or positive. So A12 is equal to minus 1 to the power 1 plus 2 times determinant A21 times A33 minus A31 times A23. Right? This is it. And now let's see the example and with the numbers. Where is the number? Give me an example. Yes, these are our numbers. Let me take again this screen. This is our example. So let's say take the first row. When you're taking the first row, we are talking about 2, 5, and 4. So it means determinant of A is equal to 2 times A, I will say 2 in this case, and then plus 5 times cofactor of the 5. 5 in this case is 1, 2. And then 4 times cofactor of the 4. 4 means the element 4 is here, and removing the column and row will give us the cofactor of the place which 4 is belong to. So the way we do is 2 times minus 1 to the power 1 plus 1. Location is 1 plus 1, right? it is 1 plus 1 is 2, times matrix, determinant of matrix, this one, I will say like this, so we show the matrix, plus 5 times minus 1 to this location A5 is actually the first one, second column. It is 1 plus 2, it means 3. So 1 plus 2, it means it will bring the minus for us. And then when we remove the first, second column and the first row, then we have 3, 2, 5, 6. And then plus 4 times 3, 1, 5, 4. What does this mean? This means take the element 4 and remove the column and the row. Let me delete the other part so we can see. So this is the 4 we are talking about now. And then we assume that we remove this column and this row. And this is the matrix left for the minor and determinant of that minor means 3, 1, 5, 4. So now this means 2 times the determinant of this small matrix is 6 times 1 minus 2 times 4. So it means 6 minus 8. Then comes 5. But of course, the sign is cofactor of sign is coming as negative. So minus 5. And then this 3, 6, and 2, 5. 3 times 6 minus 2 times 5. Right? Yes. And this means 10. And this means 18. And then plus 4 times 3 times 4, 12, minus 1 times 5. 12 minus 5. And this will be equal to, this is equal to minus 2, is equal to 8, and this is equal to 7, and this means minus 4. I don't want to go next page so we can see the screen, and I am not able to make continuous flow paired pages. I don't know how it looks like now. I will figure out later. So then I will add another color so we can I will make it a blue. So 2 times minus 2 is equal to minus 4, and 5 times 8 minus 40, and then plus 28. 44 minus 28 is minus 16. So let's go to the page. So this is the determinant of A. So if you go to book, let's see the book example, and I will take the screenshot and bring it to our notebook so we can talk about it. And this is our example, and this is summarizing everything. So it says determinant of A is A11 times excuse me, a cofactor of A11, and then A12 times cofactor of A12, A13 times cofactor of A13. So if you go through this calculation, just we did more detailed above, and the result is minus 16. So this clearly shows how you are able to get the determinant of a matrix. If this is not equal to 0, it means this matrix is not singular. If not singular, there is a good point of it. We'll talk about it later, but generally it's inversible, and it means you are able to make like identity matrix. You are able to make operations on it so that you are able to single out by diagonal matrix, and from there you are able to solve it if it is solving some system of equations, it is solvable. There is a solution for it. And like here, example 2, it's on the left. I will see if there is anything we have to talk about it. It says you are able to do same thing for any row or any column. In this case, it is choosing, and let's see, second column, second column means, let's go back to our matrix on the right and see how it is done. So let's take the screen again. So in this case, it is taking the second column. So the elements you are multiplying is this one and this one and this one. So this one, this one, and this one. If you look at the ij, it is 1, 2, and then 2, 2, and then 3, 2. It means our signs will be depend on this script, which means subscript, which means 1 plus 2, 2 plus 2, and 3 plus 2. So this is odd number minus, this is even number plus, this is odd number minus. It means in this case, our three terms, when we are doing the determinant, we are saying it is A12 times cofactor of A12 plus A22 times cofactor of A22 plus A32 times cofactor of A32. So in this calculation, we are hiding A12 so that we can find the cofactor of A12. And if we are trying to make a cofactor of, you want to make a cofactor of A22, A22 is here, A22. So cofactor will be coming from erasing the column and the row of the 2, 2. So it means the determinant of 2, 4, 5, 6 is the question. And when you come to A32, we are talking about A32 is here. Then to find the cofactor of A32, you have to hide the third column, third row, and second column. So it is 2, 2, 3, 4 matrix. And then look at the determinant calculation in the book on the left hand side. I will also copy that one and bring it here. And here you can clearly see how minus is coming from the sign and calculation we did here. Let me make it red in this case. Where is red? It's here. So this minus is coming here, and this plus is coming here, and this minus is coming to here. Then this is the number itself, 5, and this is the one coming from here, and this is 4 coming from here. And the cofactors are shown above. I show it one by one. And then when you go here, you can find the cofactor of 5 is 3, 2, 5, 6, 3, 2, 5, 6. And this is shown already here, 2, 4, 5, 6. And this is shown here, 2, 4, 3, 2. And this calculation is easy because you know that the determinant of two-dimensional matrix is 3 times 6 minus 2 times 5, which is this one. 2 times 6 minus 4 times 5, which is this one. 2 times 2 minus 3 times 4 is this one. And the result will be the same number. It means you are able to calculate the determinant of A by choosing any row, any column, And then if you are consistent with your calculation, most important part is the sign, able to find the sign. So you should be able to do it without any problem. And instead of thinking complex each time, generally you will come across to three-dimensional problems. And then if you just make a table of ij, I plus j, you will see that this is 1 plus 1 is 2, 1 plus 2 is 3, which is odd number, minus, plus, minus, plus, minus, plus, minus, plus. So if you take this column, for example, the first part of the calculation will be sign of positive and then negative and positive. If you choose this row, positive, negative, positive, and this column which already did minus, negative, positive, negative. That's the way it goes. So now talking about general definition of this determinant calculation, it says element times its cofactor. On the left side, we are now on the left side. Cofactor times that element, cofactor times other element, it goes until n. It means this calculation can be done for any dimension, but of course, if it is 4-dimensional, what happens? 4-dimensional, if it is 4-dimensional, I don't know this example here. I will not go with the generic, but I will go with the numbers, only showing the location of the elements. So let's say you are talking about this matrix, and you want to find the determinant of it. And determinant of this matrix, forget about the zeros and the point in the book right now. I'm talking about the general matrix. So if you choose like first row, what was definition? Definition says the element times it is cofactor. Cofactor means this matrix, determinant of this matrix. So when you're talking about determinant of this 3 by 3 matrix, it is like the problem we already defined above. You take a row and then you calculate its cofactors for each element of that row, and then you keep going. It means 4-dimensional, like 1, 1, 1, 2, 1, 3, and 1, 4. 4 elements you took, and then you say, I will be multiplying this by cofactor of A11, cofactor of A12, cofactor of A13, cofactor, and cofactor of A14, right? But cofactor of A14 means something like A22, A23, A24, A32, A33, A34, and A42, A43, A44. This is coming from hiding the A11 row and column, and the rest are here. But this itself, we have to calculate the sign of it, then determinant of this matrix, right? So we say sign is minus 1 to the power 1, 1, which is 2, which is plus. Then determinant of 3 by 3 matrix, right? And this is just a problem which we did above. It means without worrying about the 4-dimension, when you are calculating determinant of a matrix which is 3 by 3, you have to apply the rule exactly the same and find a unique number. If it is a non-singular, there should be a number, right? And you find it and you put it here, determinant of that matrix, and then following the signs and the elements, A11 times cofactor, A12 times cofactor, and obeying the rules, you can go from any dimension. If it was like 5 by 5, then the first row times its cofactors will be the size of 4 by 4, and each 4 by 4, you will be calculating another row times its cofactors and go until you finish it. So it looks very messy, and that's why we have to program it. For the writing the line of codes for these solutions are very simple, just making the certain loops, you go through and then you finish up. So these matrix calculations are very important for engineering problems, and mostly those problems are having a lot of dimensions, like 500 by 500 matrix. You have to solve it for certain problems, and it is possible to do it by code without too much time. But by hands, it is like disaster. And now let's see the second part. And okay, let's see this example again. So the point in the book is when you are choosing this, in this case it was, let me see. When you try to find the determinant of this matrix, you should be wise to choose which column or row you are picking up, because you can pick any row and then it means you pick the row or column which will make a minimum calculation. In this case, if I have to choose the first column, then 0 times the rest. Forget it. We don't need it. We don't have to calculate it. We don't have to do anything. So only calculation will be on for this element. So that element means like A for 1 times cofactor of A for 1. And that means 2 times cofactor means minus 1 to the power 4 plus 1 times determinant of it is cofactor. Cofactor is when you hide this column and row, this is the cofactor. Now we have to find out the determinant of this. How do you find the determinant of this? If you choose this column, you have to make 3 calculations, right? But if you choose this column, then you have to do only 1 times. So then independently, this means 3 times it is cofactor. Cofactor, I will change the color here. I will make it green. So cofactor of 3 is this part, right? So it means 3 times 2, 3, 4, 5. But we need a sign also. What is the sign here? This is 3 by 3. It means minus 1. 3 plus 3. It means 6. It is plus. There is no sign coming from this part. This is 3 times 2 times 5 minus 3 times 4, and which means 12, 10, minus 2, and this is minus 6, right? If I am not wrong. Then this is just the determinant of this section. So there is a sign here which is coming minus, and totally it is minus 2 times minus 6, which is equal to 12. This is the answer. So probably you will come across many different matrices, and you have to pick the right column or row to minimize the calculation. This is the trick. I am repeating, if you are giving a complex matrix, you should figure out how to choose the right column or row for your operation of finding the determinant of that matrix, so that you are able to make minimum calculation. In computers, it is still important, because if you have 1000 by 1000 matrix and you have to repeat calculations, and you are able to improve your code by saying, I will not do the calculation if the first multiplier is 0. You don't have to go through the function and then multiply them first and then see the result is 0. No, you directly check the mark and say if the element is 0, then you don't go through the multiplication. So you save the operation time, and this can also save computer time. And it's also important to figure out which column or row you should pick for the calculation. And I think I will stop it here and continue next.